Okay, YouTube, in this video we're going to discuss a really important theorem called the rational zero theorem and how it applies to finding x-intercepts or finding solutions for polynomials that happen to be a really, kind of a higher degree, so like, third degree, fourth degree, or above. So let's go ahead and introduce what this rational zero theorem is, and I'll go through an example of how we apply that. So it says here we have the polynomial function f of x equals this, or y equals this, and you notice we have some third degree polynomial here, and the leading coefficient is 64, so we can determine things about its end behavior. But I go ahead and tell my audience here that these are the zeros right here, and as a matter of fact I list them out already, and by zeros, remember, these are x values that when we plug them in we get a y value of 0. And another way of saying this is when you graph something, these are the x-intercepts that we're after here, okay? So basically, if these are the zeros of this function, the thing I want to point out here is it says, notice that the numerators, of these zeros are -3, -5, and 7. Looking on the top here, -3, -5, and 7. And we say these are factors of the constant term -105. Now, I wouldn't expect the layperson to recognize that they're factors of -105 because it's kind of a larger number, but they are indeed factors of this constant term right here. And the interesting thing is 2, 4, and 8, these denominators down here, those are factors of the leading coefficient 64, okay? And this always tends to happen with polynomials that if you have rational zeros, we say a rational zero, remember, anything that can be written is a ratio. A whole number over a whole number is a rational number. I'm saying if you have any answers that are rational like this, like -3 over +2, or -5 over 4, or 7 or 8, 7 over 8, then it has to be the case that they are the factors of the constant term over the factors of the leading coefficient, or all the possible ones. So we say if f of x is some polynomial here, and I just want to point some values out here. We say a sub n, this is the leading coefficient. So you'll want to list that there. That's called the leading coefficient. We really care about that, as a matter of fact. It is on the dominant term. And then we say the degree, okay, of the polynomial at least. Every term has a degree, but the degree of the polynomial is this n right here. And then the last thing I want to point out is we say this a sub 0 back here, it has no x on it. We could write times x to the 0, but we don't need to. But this is the constant term, okay? But the two terms we're going to pay most close attention to are the constant term and the leading coefficient. And we say this. We say if f of x has all integer coefficients, that is, this polynomial up here had 64, 120, -34, and -105, and those were all integers. Those are all whole numbers, positive or negative, or say 0. It says, then every rational zero, that is every zero that can be written as a fraction of f of x has, it's supposed to say has here, has the following form. So basically what this is saying is, here, if you have integer coefficients in your polynomial, then if you are even possible as a rational answer, like if I can even get you, then you have to be in this sort of format, okay? And where we say it's p over q, so here's our rational values, but we say it's really p representing the factors of the constant term, and that was this back number right here, over the factors of the leading coefficient, which is this a sub n here. So basically what I want to do is I want to kind of put this to practice for you and show you what I mean. It says find the rational zeros of f of x equals, we've got this third degree polynomial with a leading coefficient of 1 and a constant term of -12. So I say, well, let's do this. If I wanted to solve this, first of all, what would I normally be doing? I would set y equal to 0. Remember, we're finding x-intercepts, so you set y equal to 0. And then the first thing I try to do is I would try to group this out. So I'd say, well, could I possibly solve this by grouping it out? And we can try here. We say x squared, x plus 2, and then here, the only thing I have in common, I suppose I could take out a -1 here, and then say I got 11x plus 12 instead. But you notice that these don't match. So the point here is this: when I can't do this by factoring, which would have been nice, perhaps we could divide out a factor, and what this is doing is it's giving a list of factors that might possibly work first. So what we're going to do is this: we're going to list the possible rational roots. This is how I normally write it. Now you probably list it, but we say plus or minus out front, and then we'll write this. Now this tang means the set of numbers, so we're listing the possible rational zeros for this. Now I'm going to put my division bar in here right in the middle of this, but we'll say this. Actually, I want to put my plus or minus on the inside, but the set of plus or minus division bar, and we're going to list the factors of the constant term. So now the factors of 12 are 1 and 12. We say 2 and 6, 3 and 4. So I think we've got them all here. I just want to list them in order. We say the factors of leading coefficient. Well, factors of 1 are 1. So we say what are, and I'm going to write an equal sign here, what are the possible rational roots? We say plus or minus now 1 over 1, which is 1, plus or minus 2 over 1, which is 2. Everything of over 1, essentially, we're going to put over 1 individually. And we say these are the possible rational things that could go into it. So if these are the things that could possibly go into it, here's our goal. Maybe we could get one to divide out. Say, go in evenly, and what that would do is it would leave behind another factor that's also a factor that we might be able to factor on our own without dividing any longer. So here's what we'll do. We're going to do synthetic division here. Recall that with synthetic division, your polynomial needs to be written in standard form, and we need its coefficients. So I'm just kind of rewriting what we have up there. And I notice I have all my terms here, an x cubed, x squared, x to the first, constant. So when we do this, we do not need to fill in any zeros here, but we say 1, 2, negative 11, and negative 12. And what I'm going to do is I'm going to start by saying, well, if it's a possible rational zero, then it's got to be in this list right here. This is what this is. It's a list of possible answers, essentially. List of possible answers. So what we're going to do is we're going to pick one out. I always start with positive 1. It's an easy one to evaluate for. We say, is x equals 1, is this a 0? So I'll write this 0, question mark. We have to check to see if we plug this in, do we get a remainder of 0, essentially. So that's the question we're asking here. I'm going to take that out for now. So we say, carry down the leading coefficient. So we'll multiply diagonally. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. 3 plus a negative 11, I get negative 8. And then negative 8 times 1 is negative 8. You notice here that we get negative 20 on this back term. So essentially what this means is this is not a 0. X equals 1 is not a 0. And what I'm going to do is I'm actually going to go back and say, well, that gets rid of possible answers. It gets rid of positive 1. So what if we tried negative 1? So let's try this again. We'll carry down our leading coefficient. We say negative 1 times a 1 is negative 1, plus a 2 is 1, times a negative 1 is negative 1. So this time, look at this, we get negative 12. And take that times a negative 1, we get a positive 12, which leaves behind a 0. So here are the things we want to comment on here. We were asked to find the rational zeros for this. So we say, in terms of my answers, I know that right now, I was able to discover that x equals negative 1 was one of my answers. Now, a few things we know about this. If x equals 1, negative 1 was one of my answers, then x minus 1, this was a factor. Remember that when you set factors equal to 0, like if I said, well, if that was a factor, then I would have set it equal to 0. And if I would have set this equal to 0, I would have gotten plus 1, plus 1. I would have gotten x equals 1. So we say if, x equals, this was plus 1 here. This has got to be plus 1, because this is negative 1 here. They're backwards, okay? So, but when I subtract this from both sides instead of add, okay, then I get x equals negative 1. So essentially, here's our factor. But furthermore, we say when we synthetically divide, remember this thing right here, this is the remainder. And this right here is the quotient. This is the quotient, okay? So when we say this is the quotient, we'll put things back. We say 12 is our constant. This is our x to the first term. This is our x squared term. So we have 1x squared plus 1x minus 12 coming out of this quotient. But what this means is really the original polynomial could be written by the thing we divided out, this factor x plus 1, times this factor right here. So we say plus x minus 12. The nice thing about this is now we can just go factor this. So we'll carry down this x plus 1, and we'll go factor this if it's factorable. And I notice that this is indeed factorable. We say x plus 4, x minus 3. So if all of this now, if we were solving this and we said we want this all equal to 0, let's go solve this. Now we can set each of these factors, this times this equal to 0. Set each one equal to 0 individually and go solve them. And one can see how we could easily conclude, again, if these are the factors, then the zeros are just opposite these. So we say negative 1, negative 4, and 3. So very quickly, I want to go look at the graph of this. We say these are zeros or x-intercepts or solutions, whatever you want to refer to them as. But I did graph this, and we can see here, if I fill this in, we have a third degree polynomial, so that's odd. So our end behavior on the left and the right is different. We had a positive leading coefficient, so it ended up on the right side. And if we zoom in here, we could say, what zeros did we find? So we say, what are the x-intercepts here? I'll click on them. So negative 4 was one of the x values. Negative 1 was the other x value, and then positive 3 was the x value. So we could see how we arrived at this using the algebra of it, but what we have to do first is generate this list of possible rational roots, which is what this video is about. Cheers.